All right, today is the first lecture on our next unit, which is on solutions. Um, Solutions is looking at where we have a mixture of multiple substances put together in which they are, one can dissolve in something else. Now, up above and the top, I've drawn a picture here of a water-based. Now, almost all the solutions we're going to talk about in this unit is going to be water-based solutions, things that dissolve in water. Water is considered the universal solvent. And the solvent is the substance that dissolves the solute. As you can see in the very bottom, list of terms. Well, there's some vocabulary terms you need to be aware of. And so this page is very critical in understanding what concepts to know. So the solvent is the dissolving medium. What dissolves the solute? And for this unit, almost often it's going to be water. Secondly, sometimes when you're not sure which one could be the solvent, which could be the solute, it's the one that's in larger amount. So if you know the multiple things that are mixed together and they're dissolving in each other, the one that you have more of is going to be considered the solvent. The solute is the substance that dissolves into the water. And it can be a gas, it can be another liquid, it could be a solid. So that is called a solute. So the solute would be little particles that are suspended in the water. And the mixture together, the whole thing, is called the solution. Okay, so a solution is a homogeneous mixture. Homogeneous means evenly distributed, which means when you look at it, you can't tell that it's a mixture. Okay, when you add salt water is a classic example of a solution. The salt, when it dissolves and dissociates into the water, you can't see the individual salt crystals being suspended in the water. You can taste them, but you can't see them. And so when it looks evenly distributed, as if there's only one phase, looks like there's only one thing there, that is called a homogeneous solution. Okay? If you can see multiple phases or multiple situations, then it's heterogeneous. Okay? So an example is if you would have a test tube and there's some liquid in it and then there's solid in the bottom. Okay? When you can see more than one phase, more than one state of matter, then that would be called heterogeneous. If you cannot, if there's only one phase, then it's homogeneous. Okay? Now, there are multiple different types of homogeneous mixtures. They can be gaseous, they can be liquids, they can be solids. Okay, real quick, if you want to pause lecture, think of one in each of these situations and see if you get them right. The classic gaseous mixture is simply the air that we breathe. Air is a mixture of more than one gas. When we look at air, we can't tell that it is a mixture. We can't see the individual gas particles. And air is primarily composed of nitrogen and oxygen. And there's about 79-80% of the gas is nitrogen, and about another 18-19% is oxygen. So in that situation, who would be the solvent? The nitrogen would, because it's the one in the greater amount. So we would say the oxygen is soluble in the nitrogen gas. Okay? A liquid situation, okay, could be any two liquids that are soluble in each other. An example here would be alcohol and water. With our current pandemic, okay, some of these isopropyl rubbing alcohol solutions, there's some water in it as well. That would be an example of a homogeneous liquid solution. And then a solid situation, which is even tougher, would be something like an alloy, a mixture of more than one metal, or a non-metal with a metal that's soluble like carbon steel that's in a solid state, solid phase. That would be an example of a homogeneous solid mixture. Okay? Now there's three ways to classify a solution. And that is it unsaturated, is it saturated, or is it supersaturated? An unsaturated solution is holding, it's not holding the maximum amount of solute. It could dissolve more. So if I'm making a sugar water solution, if I dump more sugar into it and it dissolves, the previous state of that solution was unsaturated. Saturated means we are holding the maximum amount. Okay, we are in what's called a state of equilibrium. Adding any more solid will not dissolve. We'll have some solid sitting on the bottom. Okay, so an example of that, if I have a beaker and I have a saturated solution, okay, and I add more solid, we're going to see the solute sitting on the bottom, not being able to, we can see physically see that it's not getting any smaller or larger, And in that situation, we know that the solution above it is in a saturated state. Now, I say it's in a state of equilibrium. Why? Even though it doesn't look like anything's going on, this is a dynamic system. Some of the solute is dissolving and going into the solution, okay? And then some of the particles that are suspended in the liquid collide with each other and they recrystallize back out of the solution. So if you're able to look at the molecular level, this substance is constantly dissolving and recrystallizing back and forth. These two things are going on. We just can't physically see them. But if we're in a saturated solution, what do we know about how quickly the solid is dissolving or recrystallizing? They're equal. So in a saturated solution, we have a state of equilibrium because just as much solute is dissolving as what is recrystallizing out of the solution, meaning physically when we look at it, it looks like nothing is actually happening. Okay? A supersaturated solution, these are quite rare, but they are possible. In a supersaturated solution, we have more solute being held than what theoretically should be being held. Any small disturbance will cause that excess solute to recrystallize out of it. So let's say the supersaturated solution is holding 20 more grams of sodium thiosulfate than it should at the current temperature. Okay, if I were to shake it or agitate it, sometimes I've even seen people scream at it, the vibrations of your voice could cause enough of a disturbance that will cause some of that solute now to start recrystallizing. And once it starts to recrystallize, any excess solute that's being held by the solution will come out of it. Okay, and that pile of solute will then sit in the bottom. The remaining solution would be a saturated solution. Not all the solute comes out, just the amount of excess comes out. The remaining solution is still a saturated solution. So those are called supersaturated. All right, so one situation I could do is in class is I could literally give you a test tube of different solutions and ask you how can you identify if it's a saturated, unsaturated, or supersaturated solution. What you would do is actually call that a seed crystal. If you knew what the solute was, you would add a seed crystal to the solution. Now, if it was unsaturated, what would happen? It should dissolve. Because if it was unsaturated, it should be able to dissolve more. So if the seed crystal dissolves, we know that the solution was unsaturated. If the seed crystal ends up growing and getting bigger and bigger and bigger, and now we have a huge pile of solid sitting at the bottom, what does it tell you about the original solution? It was supersaturated. If more solid comes out, if the crystal gets bigger, then it was a supersaturated solution. How do I know if it's saturated? I add the seed crystal and nothing happens. The crystal stays the same size, it doesn't dissolve, it doesn't get bigger, then the solution was saturated. It was at the maximum capacity. So that's an easy way we can determine if a solution is unsaturated, supersaturated, or saturated. One little seed crystal could tell us what type of solution it is. Okay? How do we make a supersaturated solution? Well, it's a process. We have to heat the solvent up because usually when we heat solvents up, they will dissolve more solute. Then we cool the solution down very slowly, just letting it sit in the air. And as it cools, if it is a substance that will supersaturate, as the solution cools, it will not be able to hold as much solute. But some substances will stay in a state of supersaturation, and therefore, even though it shouldn't be held, it stays suspended in the solution, even though the cooler temperature now shouldn't hold as much solute. Okay, now we've created a supersaturated solution. And as I said, if we just add one seed crystal now, that little disturbance could cause any excess solute to come out of it. Okay, so down below we have a few more terms just to be aware for the test. Okay, solubility is going to be the maximum amount of solute that will dissolve in 100 grams of water. So solubility is really tied to saturation. What's the maximum amount of solute that will be held in that amount of solvent? Something that has a high solubility in a solvent is called soluble. Something that doesn't have a very high solubility is insoluble. Nothing is truly insoluble. Okay? So even if I put metal into water and nothing happens, a small amount of the metal particles on the surface will go into the water, but it's just such a low amount that we say it's negligible. Concentration is the next lecture I'll talk about, which is going to be on what types of things we use to measure how concentrated, how much solute is in a solvent. Aqueous means that it's something dissolved in water. And again, most of this unit we're going to focus on aqueous solutions. Equilibrium, we've talked already about. Miscible and immiscible are only used for liquids. So alcohol and water are miscible in each other. They will dissolve in each other, forming one phase, homogeneous solution. Think of an immiscible set of two liquids. Hopefully some of you thought of oil and water. And if I put oil and water, I have two phases. I have the oil layer on top and the water layer on the bottom because oil is less dense. That too would be an example of a heterogeneous mixture, okay, because of being able to see multiple phases. And then solvation I'll talk about in a second. So let's turn the page. So today's big goal is being able to read solubility graphs. And here's an example of two solubility graphs. Now this first one is looking at solid solutes in water. And if you look at them, what's the general trend that we see for almost all solid solutes in water? As the temperature increases, what happens to the solubility of it? They increase. So solids, their solubility tends to increase with temperature changes. The second graph is looking at gas solutes in water. Gases in water. What do you see about that trend? As temperature increases, the solubility of gases is decreased. Okay, so water will hold less gas, and this is partly why in the summertime you might see fish die in like a lake or reservoir, especially shallow parts of the lake. If we get a lot of hot, dry weather in those shallows, because the water is warmer, it doesn't hold as much oxygen, and the fish are literally suffocating. Okay, so that is an example of how we can see where gas is. So colder water holds more oxygen than warmer water does. Okay, so each of these lines, the line itself is the saturation point for that substance. It's the amount of solid that will be held by, in this case, 100 grams of water, which will be typically the case in this unit, okay, at a specific temperature. So now we have to know the amount of water and the temperature to be able to do these solubility type of problems. And again, the saturation point, this line of solubility, this is the solubility of the material. The solubility is the saturation point, the maximum amount of solid that will dissolve. Okay, so if I add amount of solid that's below, okay, let's look at this yellow lead nitrate line. If I add amount of solid that is below the line of saturation at that temperature, what type of solution will you have? Unsaturated. If you're on the line, it'll be saturated. If you're above the line, it actually depends. I know you're going to say it's supersaturated, but it depends if that substance forms supersaturated substances. If all you do is dump a whole bunch of lead nitrate in water and it goes above this line, you will not form a supersaturated solution. You've got to have that ability to heat the material up, have that line get above that amount of solid, then let it cool back down. And lead nitrate is a substance that does not form supersaturated solutions. Therefore, once we drop below that line, you're going to start to see crystals grow in the solution. So it has to be a material that supersaturates. So on the test, if I don't state that all of that solid is dissolved, if all I do is I dump an amount of solute that goes above the line and I stir it, the water will only dissolve up to that line, no more. The excess solid is the amount of solid that does not dissolve, that will sit in the bottom of the beaker. We have a saturated solution. So more often than not, if we're above the line, we're really saturated. The only time it can be supersaturated is if I explicitly tell you that. All right, so to do these problems, you have to know, problem A, you have to know what the solute is, the amount of water, and the temperature in order to do these problems. Because I want to be able to tell where I am at in conjunction to that point of that solute in water. Okay. Now, one thing about this unit, 100 milliliters of water is equal to 100 grams of water. Okay, why? The density of water is 1 gram per milliliter. So 100 milliliters of water is 100 grams of water. Okay, something just you to be aware of on this. If you ever see milliliters, you can easily cross it off and put down grams. Okay, so at 60 degrees in KBR, we got to find the KBR line here. Which for some reason it's not on here. I'm not sure why that's the case. All right, I think when this was put up here by Ms. Fassler that this was an old set, so I'm going to change some of these. So let's change this to KCL. Okay, how many grams of KCl will dissolve in 100 milliliters of water at 60 degrees? Okay, so what I need to do is find the KCl line, and I got to find 60 degrees. And when I go up there, I make the point, and I go across, and it looks like 45 grams. Okay, so about 45 grams of KCl will dissolve in 100 milliliters or 100 grams of water. So that is the saturation point, that is the maximum solubility at that temperature. Okay, if 80 grams of KBr is added to 100 grams of water, will it dissolve? Okay, so if we look at the line for, and again, I'm going to cross out KBr and put KCl. If 80 grams of KCl is added to 100 grams of water at 30 degrees, will all of it dissolve? Well, if I find KCl at 30 degrees, we'll notice that the line now is at about 35. Will all of it dissolve? No. Okay, it will not all dissolve because the water at 30 degrees can only hold, okay, about 35 grams. 80 grams is much bigger, so of that 80 grams, only 35 will dissolve, which means if I subtract, about 45 grams will sit at the bottom of the beaker. It will not be dissolved. Okay, so what type of solution do we currently have right now? If it doesn't fully dissolve, it is a saturated solution. Okay? If the water is heated to 80 degrees, will it all dissolve? Okay? If I look at 80 degrees, KCl, we've changed it because KBr is not on here. And we'll notice that the line still only goes up to about a little over 50 grams. 80 grams has been added, so still the answer is no. Okay, so what type of solution do we have? We have a saturated solution. Okay. If the solution is cooled back to 30 degrees, and again, these don't really work too well, so I'm going to change things up here. All right, so I used a little bit of that time to write a few new questions because I wasn't really happy with some of the questions presented on this page. So here I got a couple other questions that you can just look at quickly and answer, and if you, again, pause the lecture whenever to be able to answer these questions. Okay, so the next question I wrote up here is, at what temperature is the solubility of sodium chloride and potassium dichromate the same? If you want to pause the lecture and answer a question, great, but then I'll go through the answer here in a second. So if I look, what I want to do is find the temperature where they're the same. Well, when is the solubility the same? Well, that's going to be where the two lines meet. So if I find NaCl, which is that light blue line, and potassium dichromate, which is the purple line, they meet right about right here. Dropping down, it looks like they meet at about 60 degrees. So on the quizzes or tests, the answers will be quite spread. I might have like 40 degrees Celsius, 50 degrees Celsius, or maybe 50 degrees, 55, 60, 65 degrees Celsius, where, again, if you are paying close enough attention and detail enough, you should be able to easily see what the answer is. I'm not going to have like 58 degrees, 59 degrees, 60 degrees, 61 degrees. I will not do that to you. There'll be a wide enough spread that the answer should be quite easy on the multiple choice. Okay? Next type of question. If 30 grams of potassium chlorate at 30 degrees is added to 100 grams of water, how much solid is not dissolved? So again, we've got to find the potassium chlorate line, which is right here. Okay, we're at 30 degrees. So in all these problems, the first thing you want to do is find where the line is at that temperature. So for potassium chlorate at 30 degrees, the line is at around 10, which means it will dissolve 10 grams of potassium chlorate for every 100 grams of water. Okay, so we have 100 grams of water, so it matches perfectly, but it's 30 grams. Okay, so 30 grams is up here, but we can only dissolve 10. So if we subtract, we get 10 grams of excess, and that will be the amount of solid that will not dissolve. So the answer is 20 grams. Now, lastly, what happens when they change the amount of water? If the amount of water is changed, we now have to use a proportion, because 10 grams in 100 grams of water is the same concentration as 30 grams in 300 grams. So whenever the amount of water changes, or they ask for the amount of water needed to dissolve this amount of solid, you're going to utilize a proportion. So in this problem, it says 50 degrees in potassium dichromate. At 50 degrees, potassium dichromate is right at 30. Now, for some of you guys, you're smart enough, you probably could easily do this math in your head. You wouldn't have to necessarily do the proportion, but 30 grams will saturate 100 grams of water for potassium dichromate at 50 degrees Celsius. So find where the line is at. This number comes from the graph. Always write that down first. Then create a proportion. What do we know about the new solution? We don't have 100 grams of water, we have 300 grams. So now we can solve for x. And because we're simply tripling the water, you guys can probably already see we just need to triple that, and we get a value of x of being about 90 grams. It'll take about 90 grams of potassium dichromate to saturate 50 degrees water at 300 grams of it. Okay? But again, if you couldn't do it in your head, you'd use your calculator, you'd cross multiply. 100 times x equals 30 times 300. Divide by 100, and you get your answer. Okay, so if the amount of water is not equal to the graph, 100 grams, if it's not equal to 100 grams, you're going to set a proportion. Find where the line is at that temperature, write it down, write it as solute over solvent, and set it equal to the amount of water or the amount of solid that they give you in the problem, and then solve the proportion. That's how you do these problems and the harder ones on the homework for tomorrow. The next page is concepts that I'm going to do in a different lecture that I'll post that is not needed for this test that you're going to take. This is going to be an extension. For those of you that are thinking about taking AP or have signed up for AP Chemistry, you might want to listen in on this lecture on page 4, just so you kind of get some of the other concepts that are more geared towards AP. But for this unit, I've pulled this out just to try to minimize what you have to know, especially with not being able to meet with us daily. Okay? The last thing to look at in the very last page, on page 5 here, is factors that affect solubility. What are some factors, key factors that affect how soluble something is and how quickly something will dissolve? Now, there's 2 key questions. Look at this. How much or how quickly? Okay, how much is looking at the overall solubility of the material. Will the factor affect the amount of solid that it will dissolve? Or is the question asking how quickly will it dissolve? That's looking at a rate of solubility. How quickly, or I should say probably, a rate of dissolving. How quickly is the material dissolving and going into the solution? So be careful in a couple of these factors. Is it talking about the amount of solid that will dissolve or the rate at which it will dissolve? Okay. Now the first set of questions is looking at rate, how quickly something will dissolve. And the first one is particle size. If I have a big chunk or cube of sugar, or I've got a pile of granulated sugar, like you'd have at home, where it's the little tiny crystals. If I were to add the same amount of solid, say 1 gram and 1 gram, one's in a cube, one's in granulated form, small crystal form, and you put it each into 2 separate cups of water at the same temperature, will they dissolve the same rate? The answer is no. Okay, so the granulated sugar will dissolve faster. Why? Surface area. Because they're smaller crystals, when you pour it into the water will have more contact points with the smaller crystals of sugar. On the cube, it can only touch the surface, so much of the solid inside isn't coming in contact with the water, it won't dissolve as quickly. So the rate increases when the size of the particles are smaller. So the smaller the size of the particles, the faster a substance will dissolve. Okay? Stirring, agitation. If you stir a material versus one you don't stir, the rate at which it will dissolve will increase. These are things you probably are well of. You've known this your whole life. You've done that. Stir a solution, and because of that, it will dissolve the solid faster. Like if you're making Kool-Aid from adding sugar to water and then the package of the flavorings. So stirring will cause it to dissolve faster. Agitation. Okay, putting a cap on it, shaking it. Those things will cause it to dissolve faster. However, neither of these 2 things will cause it to dissolve any more. There's a maximum amount of solid that will dissolve if it's sugar and water. So while shaking it or making the particle smaller will make it dissolve faster, it doesn't mean that more of it will dissolve. Okay, we'll just get to the point of saturation faster. Temperature. Temperature, however, is something that can affect both the rate and the amount, the solubility. So temperature can do both. It will cause sometimes it to dissolve faster, and it can cause it to dissolve more or less. Okay, so for solids, as we saw in the graph on the previous 2 slides back, for solids, if you increase the temperature, they dissolve faster. This is why usually you'd warm up water to have it dissolve faster. You're making like a chicken broth from a bouillon cube. Get the water hotter. The hotter the water is, the faster it will dissolve. This is typically true for solids. But not only will it dissolve faster, heating it will also usually cause the solid to dissolve more. As we saw on those solubility curves, almost all of the solids, they all went up as temperature increased. Gases is the reverse process. Increased temperature causes a decrease in solubility. Warmer water will hold less gas. And that's because the gas particles are moving faster in the solvent, and they have more kinetic energy, and they have more energy to be able to break the intermolecular forces holding the gas in the liquid, and they're able to escape the liquid and break those IMF attractions. So gases are less soluble in warmer water. The last thing with gases is pressure. Pressure only affects the solubility of gases. It does not affect liquids and solids in water-based solutions or any other type of liquid solutions. So increasing the pressure will cause the solubility to increase for a gas. Okay, and this is what they do in bottling plants. When you make that bottle of soda, okay, they put that bottle under enormous pressures. Okay, you can feel that pressurized bottle. And they put a high pressure over the liquid so more CO2, more carbonation can be dissolved into the liquid, causing a carbonated beverage. When you open the bottle, you release that pressure, bubbles start coming out of the solution, the carbonation, because now we've gone from a higher pressure to a lower pressure, and less gas will be held in the lower atmospheric pressure conditions. And that's why they do that. That's how we're able to create carbonated beverages. However, pressure has no effect on solid liquid and liquid solubilities. Pressure only affects gases. And from that comes something which is called Henry's law. Henry's law is a proportion. It is what we see is because it is a direct relationship. We think back to gas laws. Whenever we have a direct relationship, the equation ends up being a proportion. When we have proportions, we have direct relationships. So S stands for solubility, P stands for pressure. So if we increase the pressure at the bottling plant, the amount of solubility that the substance will incur will increase accordingly as well. So let's say for carbon dioxide, okay, let's say we'll keep it at 20 degrees Celsius, okay? 0.10 grams of carbon dioxide will dissolve, okay, in 100 grams of water at 20 degrees Celsius, okay, at 1 atmosphere. What will be the new solubility of carbon dioxide per 100 grams of water at 20 degrees Celsius if the pressure is increased to 5 atmospheres? Okay, typically the pressures that we see in bottling plants. So using Henry's law, we'd put the solubility over the pressure. We don't know the new solubility, but we do know the pressure. It was 1 atmosphere, not 0.1 atmospheres. Okay, so again, we have a proportion graph. So Henry's law is proportion. We have increased the pressure by 5 times. So again, we can cross multiply. And we get a value that's 5 times greater. So we have made the solubility of carbon dioxide increase by a factor of 5 because we increased the pressure by 5. So this is an example of Henry's law. Okay? So the big thing to take away are some of these factors on this page, but also then the ability to be able to answer and read solubility graphs. So your homework for tomorrow, which I've put online already, and today I'll also upload the answer key to that, is you'll utilize, the homework will have a specific solubility curve at the top. You'll use that solubility curve to answer the questions below. And then if there's any questions or problems that arise from that, give me an email or any other way to contacting me through Canvas, and I'll get back to your questions. Okay? And again, on Thursday, remember, I'll have a lecture at 1 o'clock if there are some problems on this stuff. And again, Friday is the day we'll do a formative quiz to see how well you're doing on reading solubility curves. Again, thanks for listening. I apologize for the length of this lecture, but there's a lot of material to get through. So you can start and stop and whenever, and hopefully you're able to get through all of it. Okay? Thanks for listening again.